Overzealous Tom probably announced the book too soon. So if we could keep it in family, that would be great.
Yes, because I just want to say that it's kind of initial approval, still nothing official. So we will want to to wait before celebrating about that.
Yeah, exactly.
So I will share my screen now. I hope it will be quick presentation. Then we can go with hi Timo, with your examples, Tom, about the fake data. And today the session in general will be related to the data. So here we go. Let me just, okay. Now, since we are dealing with data science, that means data is the most important part in our life cycle, in our pipeline, whatever we want to name it. Why it's the most important part? Because this is our fact. This is what we are trying to extract information from it. So if our data is telling something to us, then we are able to model it. Otherwise, if we don't have the data with the good predictive values or with the good information to tell, so that means we don't have anything to do. Today we are going to speak about what is the data in general, what is the meaning of machine learning or data science in the current software life cycle and how it's categorized somehow, what is the data sample and data set, and what kind of data issues we might face. Data in general, we can name it as units of information. Now here we are able, by the way, I want to mention something. When I'm on the presentation and I'm sharing my screen, I will be unable to read the chat. So Tom, please, if it's possible, you or Giovanna, if there is any question, just please stop me and ask the question, or we can keep it after the presentation.
Yeah, I'll watch for the questions when you're talking.
Okay, thank you. So in general, previously there is let's say, scientists want to say that the data is the structured information and the information is the unstructured information. In fact, this is right now, it's changed. So the data, it's units of information only. You cannot name it structured or non-structured, because for non-structured information, we have a kind of big data appeared, and this concept appeared, and we are working and dealing with it. So the only thing that we are able to say that data is units of information, and datum is the singular of data, which is one information or one valuable value we can deal with it. Here we have to think, when we are talking about data science or machine learning using data, we have to consider what we have before that. In the previous, we have a software engineering, and there is a great softwares and great application appeared, and all of them didn't use machine learning or data science concept, because it was focusing on kind of a process. It's all about the code. You have a need, you are building a process, you are writing the code, testing it, and then you have the application is ready. This is, we name it right now, the software stack 1, version 1. Now the software stack version 2, it will be built on data. We need to extract wisdom or information or result or predictions from data with a less amount of code. So we are covering the huge size of code with data and mathematical process to get the same or maybe better result. So since we are building machine learning models to extract wisdom from data, then we are expecting that this data has to contain this wisdom. It's not coming from outside. So the quality of data is playing major role with the succeeded experiment in machine learning. So we are unable to build any model depending on any data. We will end with very strange results, something it will not be helpful. Now, according to that, the data is a start point for our process, for our pipeline, because the model is not a magic. It's not doing anything from nothing. It's depending on the facts. And this is here, it's very important. Why data is important? Let's back to our method of thinking, that we are saying that this person is emotional. He is depending on his emotion, but this one is logical. He is dealing with fact. Now, when we are dealing with data and we want to extract some information from data, we are trying to deal with fact. So the model is something dealing with fact, with data. If we don't have data can generate information and lead us to the correct result, then we don't have models at all. Models can do nothing without the suitable data to work on it. Now, we have three major tasks when we are working on any project related to the machine learning when we are dealing with data. First, we have to find and look for and seek for high predictive values of information. That means what is the most important factors, and these factors I will change the naming later to drive us to the expected result. For example, if we are talking, just remember the last week, if we are talking about the medical claims and we want to create a model to tell us that this medical claim is going to be approved or rejected. Now, this is the result that we are looking for. What is the factor for this result? We can expect that what is the patient age, who is the physician who prescribed this or who do the procedure, what is the procedure performed, and what is the diseases that the patient has. So in fact, this is high predictive values for this kind of information. Now, also we have to avoid data that didn't have a predictive value. According to that, for example, if we stuck on another example about the claim, the name of the hospital or facility name, it doesn't have any predictive value for our case. Our case is dealing with physician, with a specific specialty, with a patient, and with diseases and procedures performed. So wherever it's happened, these procedures, it doesn't make a real value unless if it's, for example, operational procedure operation and something has to be performed in the operation theater, but we perform it on the street. Now, this is for sure, it has some value, but it's not the most important. So directly we are looking for high predictive values, factors, and avoid the factors that doesn't have predictive value. And also we have to look for information that have the same feature space covering. Now, what is the feature space? This is what we are going to discuss later. Features, let's say, yes.
Just a second. Yeah, is trying to enter to the room. I don't know if you can admit her. Yeah.
Because I didn't activate anything related to admission. So,
okay, sorry.
Okay. So I don't know what I should do now. Let's try the following. I will stop sharing. See if I have any. I don't have any request. Who is trying to join?
Yeah, I'm going to talk with her with the in the chat.
Gia, I will do the following. I will make you a co-host.
Okay.
So if there is anything appeared, you can just accept her.
Thank you so much. Thank you.
I will back to the presentation. Okay. So we have this table. It's explaining medical information about the claims, the medical claims. Now, here, let's go first. We want to name these factors that I'm telling you previously. We are going to change the name and we will name it features. So what is the features? Is the information, the needed information to drive the results, to give us the expected result. So first, let's say if we have an expert who is somebody who is working on revenue cycle, medical revenue cycle, what he has to do manually to decide that this claim is accepted or not. What is the values that he is going to check? So the claim type, for example, it's one of the features. The diagnosis code, it's one of the features. Procedure code, activity ID, for example, it's one of the features. Now, all of these factors that lead us to the result, we are named features. So in general, we have the following claim dates. It's also part of the features, and it's sometimes being major rule here. So it's not something that we have to ignore. Now, so we have this kind of diagnosis type. Now, what is the diagnosis type? I will mention this information because it will help us in the practical examples. Each patient comes to the doctor with multiple diseases. He has a lot of things he's suffering from. He has initial description from his side that I have a headache, for example, But according to that, that doctor or the physician finds that he has 3 or 4 diseases. Now, one of them, it will be principal, only one. It's the most dangerous and important one we have to deal with. And the other, it will be secondary. So the diagnosis type, it's either be principal or secondary in general. We will see there is also a third type, but I'm keep it here like this because for a reason, we can check it later. Now, this is the feature. Now, what is we have output. At the end, we are going to say that this claim is accepted or not. And if it's not accepted for a reason also. Now, this is the label, which is here, the denial code. If we have a denial code, it's kind of code to tell us that each code from these, it's related to the description. So that means since we have a denial code, then this claim is rejected. If we don't have a denial code, that means it's approved. So the denial code, it's our label. It's our prediction that we are trying to do. So in this case that we are describing right now, the features we have, as we said, the claim date, diagnosis, who is the patient, claim type, or whatever, and the denial code or no denial code, it will be the label. So this is, in fact, the features, we can name it the input of the model. The labels is the output of the model. So this is it. Now, what is the feature coverage or the feature space first? Let's say the claim type. The claim type in general, we have 2 major claim types, outpatient and inpatient. So the feature space for the claim type feature, it's only OB or IP. And when we are building a model, we are expecting that our claims, all of them, it will be either OB or IP, but we will never miss one of them. That means we have to cover the whole feature space. So the feature space is the values that we are expecting the feature to cover. And in our data set, we have to cover the whole feature space because this is critical. Now, in general, given some data, a feature space is just a set of all possible values for a chosen set of features from that data. It's always possible to represent feature values and thus a feature space using only numbers. And further to do so in such a way that the feature space can be interpreted as a real space. Now, right now, we are not doing any kind of feature engineering. I'm dealing with the data as it is, but at the end, the claim type, it's a feature. The diagnosis type, it's a feature. We can then change it to numbers, just make a kind of encoding to it, just to deal with it, and it will be needed. But right now, what is the feature space for the claim type? It's OB or IB. Now, I want someone, I will never name anybody, but someone to tell me what is the feature space for diagnosis type. Hello?
Secondary or primary, principal or secondary.
Exactly, secondary or principal. That's perfect. So this is, in fact, what is the feature space, and it's one of the most important concerns that our data has to cover, our data set has to cover the feature space for all features. Now, we have to know something important.
I have a question.
Yes?
Could you please go back to the previous slide?
Okay, I'm trying, by the way, just a minute. Okay, this one?
Yeah. So
Yeah.
what if the actual feature space has one additional thing over the ones that are mentioned in the data set?
Okay,
So,
now
for example, like, yeah.
Ammar, yes, it's happening here. Now, all of these claims, it's OB, but I told you
Exactly.
that the feature space is OB and IP. Now, this is one of the problems that we have to cover. Now, this is what, today, by the way, we are talking about the issues only. We are not going to speak about how to solve these issues.
Perfect.
At the end, this is messing of representing the value. So this is, at the end, we are unable to trust the model result if we don't covering the feature, especially if the feature is important, is predictive feature. That means it's something we cannot reduce it, we cannot ignore it. So
Yeah, and
Anybody
I would
Okay.
add that Gaith also mentioned before that the diagnosis type description actually has a third category.
The
It's just
third
not
one,
seen
yes,
here.
exactly. Now, this is for the same reason that Ammar he asked about it. And the third one, in fact, it's the admitted diagnosis type, which is the description from the patient, how he is admitted to the hospital or to the clinic.
Exactly.
Okay. Now,
Perfect. Thanks.
thank you, Ammar.
Hey,
now,
Guy, real quick, I just want to add something for everyone.
yes, please.
This is a great presentation. I hope you guys are getting the feel for, I mean, just listening to Guy reminded me how long it takes to become friends with the data, to explore the data, to think through the data. Can you imagine all the permutations you have to think through when you look at all of that? And then you're there. We have to encode the data too. That's the other thing. There's so much words there. So when you look at that data, you see the value in it, but you also see the work laying ahead of you before you can even get into much analysis. It's more like, let's just start visualizing things so we know what we've got to concentrate on.
Okay, thank you, Tom. Now, I want to here to highlight something. Now we speak a lot about the data set. Now, what is the data set in general? It's a sample from the whole data that it's available. For example, if we got any example, if you want to study the blood pressure all over the state, for example, any state, or for example, here in Dubai. Now, we know that in Dubai, there is, for example, 4 million population, and for the mean value for the blood pressure is something. Now, when we are going to deal with it, we are unable to deal with all of this data or medical records for all of these 4 millions. First, it's not easy to get and collect all of this information from different institutions, that mean from Dubai Health Authority and from hospitals, from insurance companies. This is impossible to do it. Second, we don't have the capacity in our hardwares to deal with all of this data. Even you are talking about 4 million population, but if each one of them make 2 visits to the doctor per year, for 10 years, I think we are reaching a billions of records. So in general, we are dealing with samples. Now, and here the problems start to appear. For example, if we are taking 3 samples from this data, depending on for the age or the gender or any other criteria, we can find that the samples that we are select, each sample has different mean for the blood pressure. And this is that mean it's not representing really the full population. In general, we are dealing with data set. Now, here we have to know how to choose our data set to represent our case in the best way. Now, representing our case is not only to have, for example, has the same mean. Maybe even if the data set, the mean of the blood pressure for this data set is different, but maybe this data set is the most suitable one for our task because it's representing the whole categories of the society in this state. So depending on that, it's very important to know how much the data set is representing and how much it's shifted from the original population that we are dealing with. Now, in general, the data pipeline, let's back to the pipeline concept that we have. The data pipeline, it's have the following steps. We are collecting some data. We are study how to make the data ingestion, and then we are working on the preparation. Preparation, it's contain the data formatting, feature selection, and feature extraction, and for sure, data cleansing. In general, this is describing the main task for the data pipeline, which is something related to data preparation. Now here, yes, anybody want to add?
Just real quick, I'd like y'all to think, if you kept taking random samples of the same size from that last data set, and I want to come back to this next week. If you did a distribution of the means for each sample, what do we call that? And Gaith and I will answer that next week. It's a miniature assignment, basically. The first assignment we've given y'all to describe if you kept taking samples of the same size and distributed what those means were, what would we call that for next week?
Okay.
Sigmoid.
Okay. Now, and since we are dealing with data set, that means we are dealing with samples, then the issues might appear. Now, why we have issues in the data in general? This is some reasons to have issues in data, but it's not the only reasons. Also, another reason might appear during our journey and in the real life. One of them is the extract samples methods. That mean how we are extracting the sample and how we are getting the data set. Most of the time, maybe the data set, it's just offered to us. We are not extracting it. We are just studying it and compare it to some other information and to know how exactly it's helping us or not. So the extracting method, it's very important here, and how it's reflecting the statistical distribution of the original population. Also, the data creation method. What I mean by data creation, for example, if we are extracting the data set from relational database, this is structured data. Now, we are expecting that will be somehow it's clean. In fact, no, this is not, because this is coming from operational application, and this operational application, there is a lot of rules broken always, just to make the life easier for the users and for the patient, if we are talking about the medical sector. So we are not sure that this structured data is the best data that we are able to get. So how the data is created on the structured data, and even on the unstructured data, when we are dealing with this, with the medical reports, or with scripts, or with videos, now here the issues, it's expected more. That means we are dealing with a free kind of, with a free style of data. So it's expected more. With the structured data also, there is a lot of problems might be appear. The easiest one maybe, or the most expected one, it's having missed values. That means some information it's not provided at all for some samples. Now also the features space coverage. Now this is very important also, we spoke about it, that we have to be sure that our data set, it's covering the whole feature space that we are studying for each and every feature. Now this is important, and this is critical for our work. Now also the imbalanced data. Now here I want to describe it in a better way, and maybe we will visit this later in the class. We are thinking, for example, if we are talking about, let's say, the blood pressure, and let's say that we are talking about who has a high blood pressure as a disease in this population, and we found that there is 10% of the people, they have this disease. Okay, now when we get a data set and we want to build the model to predict, for example, if this patient will get in the future, prognosis model will get in the future within 5 or 10 years a high blood pressure or not. Okay, now our data has to be balanced to 10%. That means the data set has to have 10% of people who are suffering from high blood pressure and 90% who's not, or it has to be balanced on another way, which is 50% with high blood pressure, for example, and 50% we don't have this problem. In fact, here we are not looking for real world distribution to be represented. Here we are looking for better representation for the problem that we are going to study, or for the result that we are going to implement, or to offer using the model. So here it's very critical. Here in this case, we are going to find that we need 50% of the people who has this disease and 50% who doesn't. Now I'm keep it simple for one feature only, or for one output only. Now this is, but this is really critical, how to balance the data if it's imbalanced. We are not going only to follow the real world distribution, which is the main rule in our case, but then we have to find the balance according to the results that we are going to test, or to train the model to find. Also, we have noises around the predictive data. Here also, it's another important information. For example, in our previous table, we found that there is claim ID, for example. How many claim ID has to be involved in the training? Claim ID, it's not predictive information, so we can name it noise because it will choose, let's say, it will affect the signal clarity if we name the data flow as a signal in the model. So that's why we are going to focus only on the predictive data. In this case, for example, if we back to our table, the claim ID is not one of these predictive data. Now, but maybe it will be important to including in some cases. I'm not going to discuss these cases right now. Okay, and also undetected causality. Now, what I mean by that, if I'm talking about claim, it will be approved or rejected. I have to understand what is the features really needed to decide if this claim will be approved or rejected. For example, as we said previously, maybe sometimes the claim ID is not one of this information. Maybe sometimes even the physician, let's go for this physician specialty. Maybe it's not part of the claim approval or rejection unless it's not playing main role in the approval, but it's playing main role in the rejection. Because if this physician, he is not specialized to check on this patient for that kind of disease, we have to reject this claim, even if all other information is correct. So now here we have a direct causal for rejection if the physician is not specialized with the case. So sometimes we have issues to determine how the causality will appear and what is the real cause for this, let's say, for this value or for this prediction. The most also one of the reasons for the data issues is data generation method, which is something that during our process we might make some mistake, and this is also something we are going to discuss about it later. In general, this is the data issues that we might face, but not only. We might face also another kind of issues depending on the case or on the use case that we are working on. Tom, anything from your side, because I'm unable to see right now. So,
hey, I think it's going great. It's really hitting very important points about sampling data. And by the way, guys, there's a lot of bias in data that's completely unintentional. That's what I hope you're taking away from this.
okay. So we have some considerations about the data that we have to keep it. It will direct our work with data. Okay, so first and the most important one, user's need has to be translated into data. That means always when we are talking about any kind of application, either it's machine learning or normal application, traditional software application, we are talking about user requirements. Now, in data science project, user requirements are represented or translated by data, and data, it's the representation for the user requirements. This is the first. This is how we have to look to the data. Also, yes.
Real quick, Guy, I think Karen had a really good question, and I think it might have just been a confusion point. Why would we consider 90/10 balance? I think, Karen, do you want to come on and ask it just so we make sure we're really answering your question? Because it is an important one.
Yes, Karen, please.
Oh, you're on mute, Karen. Let's see if I can unmute you. I can't.
I got it. Sorry about that. So yeah, I'm just wondering about, like, you know, I understood when we got to like looking at 50/50 or taking the samples of the samples of the samples and looking at it that way. But when we talk about a 90/10 balance, that by definition sounds like it's not a balance, even though that could be a true reflection, like a representative of maybe what we see in the population. But if we're looking at predictive values and trying to, you know, having this binary classification and making that label, I would think that, and again, I don't know because I'm just wondering, but I would think that you want to have more of a balanced set so that you can more accurately predict those who are high BP, not high BP. So I was just confused.
Karen, I think you are not confused. You got my point, and maybe you are showing it better than me. Maybe I make confusion because I wasn't able to explain it well. I will make another example just to be sure that the idea is clear. Let's go back again to the original scenario that I described, that we have a set of features and we want to know that this claim is approved or rejected. Okay, only approved or rejected. We don't want to know the reason. So we have only two labels. We have only two labels here. In this case, in the real life, for example, in Abu Dhabi, in UAE, the rejection rate for the claims is almost 12%. But when we are going to represent it in our data set for this task, which is only check if it's approved or rejected, we are trying to reach 50-50% of representation. 50 rejected, 50 approved. This is the balance that we need, not the original distribution from the original population. Now, I think right now it's clear.
Yes, it is. Thank you.
Okay. The other consideration that we have to keep it in mind that the data source and data storage, how we have to be responsibly monitoring it and auditing it, either on the training or after deployment during when the model is in a practice and active, it's working. Always take care about the data coverage. We mean by that the feature space coverage. Not only on the training when we get our data set and we are sure, even after deployment. This is also, we have to keep tracking it because this is sometimes cause a problem in the future. Currently, we are in a good situation, but maybe in the future, we will have something change, which is just the case that we described for the diagnosis type. Maybe there is a third type of diagnosis type appeared. It wasn't in the original data set. So that means always we have to keep, maybe it will cause us to retrain the model. Okay, and always take care about the data balance. Now, this is the consideration always we have to keep it in mind. This is our task. This is the task of the whole team when we are building and deploying and serving the model, just to keep all of this consideration in mind and work according to it. Now, we are going to discuss about two kinds of data issues. The first one is the data drift. Now, the data drift, it's something, or we name it, maybe sometimes I name it shift. When your data set that you are used to build your model, it's not really representing the target in the correct way. Now, not about the balance, it's about the coverage more. For example, our data set, it's giving, I'm not sure if I'm mentioning example here. Oh, okay, I didn't mention. Okay. There is a difference between the data set that we use it in the training and between the scenarios that we are finding in the real life when the model is on production. So this is also why we mean by drift. That means the data set that we use, it's covering subspace, not the full space of the features. And we have, even if it was in the beginning covering that, it's changed. This is changed. For example, for any kind of values, let's say, let's consider we have a feature starting from 0 to 10 currently, and it's represented in our data set. But this is changed later, and the range or the space, the feature space, it's become from 5 to 25. So this kind of drift, it's affecting the model, and this is kind of data issues. Now, this kind of issues might appear because of the sampling method, because in our data set, in general, it wasn't accurate. It wasn't reflecting the real feature space, or it's appeared later when the model is in the production. The second kind is the concept drift. And here, in fact, it's not something, I'm not going to discuss about this diagram, this chart. I'm going to go further just to say what's the meaning of concept drift and why it's expected to appear. Now, the concept drift, it's not something that we change something on the data values or data range. There is something is totally changed. Something it's 100% it's changed. The concept itself is changed. Now, what we mean by that? For example, if we have a data set that describing transportation method, it belonged to the 19th century, okay? We are not expecting to have cars that time and airplanes, aircraft, or any kind of this. Now, here, the concept itself, it's changed. It's not drifting. It's not data drift or value drift. It's concept drift. Now we have different set of transportation methods. So this kind of change, it might appear sometimes. How it appears, as we said, it's changed on the upstream data system. If the data set it's showing trends and seasonality, what we mean by that? For example, if there is a campaign for vaccination in one country, and we get the data set during that campaign, we will find that most of the visits or most of the claim, it's related to the vaccine, and which is not reflecting, there is really changing the concept. Or now this is not seasonality, it's trend, because it's one time it's appeared. Now, if this campaign it's happening each year, for example, so we are expecting at that month, each year we will find that this peak on the vaccine cases. So that's kind of seasonality, and this is changing the concept, because if we are not if we didn't take care enough about this kind of concept, we will find that we have a concept drift. Also, sometimes
Gaith, I would, sorry, Gaith. The people I think are really getting your points, but they're asking some important points in the
Yes.
questions. I just want you to review the way I'm answering them, because I think they're getting it, but I'm afraid I might be missing a subtle point that you were trying to make. While you read those, I'm going to.
This is the last slide.
Excellent.
Okay, I'm not going to, because I think next session it will be practical example about how to solve the concept drift. Okay, from my side, and for sure you have your plan. So just the other side, it's the physical phenomena change. That means just like the example that I give it to you, or the understanding of the modeled process. Consider that all the cases appear before the scientists discover that there is a new virus which is causing COVID. What was their diagnosis for the patient case, and then the totally model process it's changed because they found that there is something new, and this is also cause a concept drift. So somehow data set before COVID, for some cases, it's not helping for studying something related to the COVID. So this is the concept drift. This is how it appears. Next week, we will discuss maybe about practicing how to solve and detect this kind of concept drift. I'll stop here and I will check your questions. I'm open for any question, and I will try to read all the message on the chat. I found 40 messages, so let me try. Okay. From where to start?
Can I ask a really quick question just with regard to data drift? I just want to make sure I understand. So is data drift something that happens when we have we train our systems on a set of data, but then because it's going into production and that new data is now live, there may be additional points that are within the new data set or the new data coming through in production that weren't accounted for in the training set? Is that what we're talking about?
Yes, this is one scenario. Let's consider the following. Let's consider the table that we have about the claims. It's our data set. In that table, we have only diagnosis type, only secondary and principal. Okay. Now, we train our model. It's in production, and then suddenly there is a new diagnosis type appeared. Okay, admitted. Okay. In this case, this is data drift. The other thing, it's the data set itself. It's not representing the facts in correct way. It's not covering this feature space. So that means the third diagnosis type, it's already there, but our data set is not covering it, and we didn't recognize it. So this is also called a data drift. I prefer people, please, if anybody has a question, it's easier to ask it than going to the chat.
Yeah, go ahead and ask any additional questions now. We one nice thing we want to take advantage of, this class is focused on you guys. So we did have something to talk about after these slides, but we don't have to get to that. We'd rather cover your questions, every one of your questions, before we move on.
Ammar, I think you have a question about, isn't
Yeah.
it a possibility that the data pairs is a mirror of the human confirmation pairs?
So I was mainly asking about the confirmation bias because it is something natural and unintentional, usually for humans, to decide and take opinion and then find the consolidations and the proofs that helps this opinion to grow and to be valid. So this is unintentional, and this is a human normal thing sometimes, until some extent. Wouldn't the data bias, which is when you hear it, it sounds like bad, but sometimes it is true, because because you are trying to make in a very wide idea, we are trying to make the machine act as we act and take decisions as we do. So wouldn't the confirmation bias be a good thing, or like the data bias be a good thing, as the confirmation bias, it is a natural thing?
By the way, I'm able to answer, but I want someone else to answer. Tom.
I was sitting here laughing because in a weak analogous sense, Amar, think of it this way. If you go out and collect the data as you're suggesting, and really all data comes from initial collections, we do tend to go, if we're learning something and we already have a particular leaning toward what we think the answer is, we do tend to go collect data to support our current beliefs. Even if we're trying not to do that, it's very hard not to do that. And so I think it gets injected, but when we allow that, I think about the way I've raised my children. I've told them, I don't expect you to agree with everything I believe or teach. I just want you to come tell me what you think differently and why. And here with the modeling, we're training the models with data that we collect, but whoever collected that data probably had some bias, were probably guided by some bias, even if they were trying not to be. I hope this is making sense. In other words, we have a bias, as I think Guy showed very strongly, just in our samples. The samples themselves are biased because they're not looking at the whole population, but in that case, we don't know the actual bias. And then as we continue to collect samples to train differently, that would be we'll illustrate this ad nauseum with k-fold cross-validation. We're trying to make sure our models generalize well so that they deal well with different samples. But in reality, let me point something out that's related to this question, but not exactly this question. Here's and I'm looking right at y'all now finally. Here's our original set of data. Now, the first type of drift that happens is more data comes in now, more features, and we're going to do a prediction based on that new data. But we didn't use this new data for training. Now our data set's this big. And if we sense our metrics going away on our predictive ability as we collect the label later, we can verify, hey, how accurate was our prediction? Well, that's a form of drift. When we see that predictive accuracy go away, and we kind of expect it because we started with a smaller sample set. But now that we've grown the data significantly, we need to pause. And this is what this class is about: retrain with that new data so we can have more accurate predictions in the future. But over time, as that training set gets large enough, it starts to represent the population more and more accurately. Now, I just drifted away from this question about confirmation bias. It gets into the spirit. Well, actually, I think you posed the question so well, Amar. I think most people are probably thinking, "Oh, I get it," but I'm curious. I should be quiet and see if people are getting it. Karen, please. Gaith and I will try to answer.
I think, yes, Tom, I think Kimberly, she was to add something before Karen. Sorry, Karen, but we came back to that.
Kim.
Kim.
Thank you. Yeah, sorry. I just wanted to clarify. One of the things that strikes me is that, you know, there's surveys, and then there's scraping, and there's all sorts of data that one brings in, and really it's dependent on the situation. If you're talking about company data that you've had, and really the size and the context of the data in terms of both confirmation bias and that drift. And I wanted to try and clarify for myself, and maybe hopefully for others, the distinction between a sort of data drift, which would happen naturally over time as more features change and get updated, or as the situation changes, and a concept drift. And really to better understand if the concept drift itself could be uncovered through, let's say, confirmation bias, for example, and realizing that there's been bias in the data, would that then imply that there is a concept shift? Thank you.
Okay. I want to speak about the technicalities. For if we are talking about the technicalities, it will never make a change if it's something appeared new or something we didn't discover before that. It was there, but we didn't discover it. So at the end, we have a concept drift, and we have to solve it somehow. Now, why this might be appear the most important thing when we are talking about concept drift, when we have something totally new appear, we are changing the concept itself. So let's say, for example, if you want to make study about the salaries in one country, and then in 1 year that there is, let's say, a rule appeared that there is no chance to change the salary depending on the nationality. It has to be only about according to the skills and the qualifications. Now we'll find that there is really concept drift appeared in the data here. Now, is it related to kind of bias it was in the past? Yes. How to translate this into, let's say, ethical method? Right now, I'm unable to speak about it. But in general, yes, this is what's happening. How there is either something it's appeared because of scientific things, or because of some rules appeared on the society. This is called the concept drift. That's all what I'm able to say here.
So would it be fair to say that a concept drift would occur if, for example, it was discovered in, let's say, medications, that a certain drug was devastating for people who have XYZ condition, and so they had to then change all of the applications that would recommend that drug to those people with those conditions, and then they would have to look at the primary, secondary, et cetera, conditions to make sure that that change is reflected throughout. Would that be a concept shift?
Exactly, Kim. And I just want to stress something I put in the comments. Oh, Gaith, do you want to?
Yes, I want to have to change between something. Either we are stopping this medication, and this is, in this case, we are not using this medication anymore. So this is kind of data drift. It's not concept drift. But if this medication is changed from one disease to another, I don't know if this is possible to happen on the medical sector, but we found that this medication we used to use it for this, and right now it's not useful for that disease. In fact, it has good impact on that disease, and right now you are recommending this for another disease. Now this is concept drift.
This is great, guys. I just want to confirm something. Oh yeah, Karen, I'm going to just say this briefly, and then we're going to get to your question. Your questions are illustrating that you're getting it, okay? But also, this is the beginning of thinking through this stuff. So you're doing great. And I want to stress, we're going to try to illustrate answers to your questions with the examples we go through in the class. So again, all I'm saying is you're getting it, but answering and properly illustrating the answers to your questions will take an entire course. And that's what this course is about. Okay, Karen, please ask your question.
I'm going to just do this really quickly because I got to jump off. But coming back to, I think, Amar, you mentioned confirmation bias. And I think one of the things that we strive for, I think, when we're looking at machine learning algorithms is how to do better for everyone. And I just say this because actually at the moment, I'm doing a lot of research and writing on algorithmic bias and algorithmic fairness, and thinking about balance and thinking about a global majority, because in most cases, we want to take those algorithms that we're working on and we want to make them extendable. But how do we extend them to other populations? How do we extend them to other people when in our culture, the bias may be national origin, and another one it may be caste, and another one it may be gender, and another one it may be XYZ. And so always trying to find ways to do better. And there's a researcher out of Stanford. Her name is Lucy Bernholtz. She's this really amazing thinker, and she says that we just need to all start at the basis that all data is biased. If we use that as our basis, then we work forward from that. That'll give us this great kind of grounding to always do what Garth is saying, to go back and test and retest, look and relook and re-examine, so that we can do better than the biases that we naturally hold as human beings.
I think that's so well said. And it is, we really need to end the class. So this was great. Garth, I really thought that was awesome. Go.
2 words only. Please, everyone, consider something, that we have a bias we are not recognizing, which is the language limit. So the bias, it's not always able to be detected. So we have to take it carefully. We are trying to do the best, to be best, but not always we are able to do that. Okay, I'm done.
I think, Karen, that was a perfect note to end on. You did great with that. Okay, I'll see y'all in mentoring. Take care.